Now, in the wild tomatoes, you can see that the flowers actually all look pretty darn similar. These bright yellow flowers, and the leaves look pretty similar. But if you can, let's see, I have a pointer here. The fruits tend to be these little tiny green things that are actually not good for you to eat. You wouldn't want to eat those. Here's that little tiny currant tomato, the Pimpinella folium that was mentioned earlier. Now, wild tomatoes have tremendous genetic diversity because they've adapted to very different kinds of ecosystems. And I was able to actually see this when I went to South America last spring. There's certain ones that are actually beyond drought tolerant. These are drought requiring, so these will not grow if you water them. So it's really very dramatic. They're the only plant out there you can see, so they're really adapted. But then there's ones that are adapted to very moist climates as well. Here's one of my favorites. There's actually 1 to 2 species, depending on who you talk to, that grow on the Galapagos Islands, and these actually have their fingers down into the salt water. So these are very salt-tolerant wild tomatoes growing on the Galapagos Islands. And then there's alpine tomatoes, and I saw these up there too. This is at about 10,000 feet, so they're incredibly cold tolerant, and yeah, they are way up there. Here's another desert species, Chilense, and I wanted to introduce you to this person who is really Charles Rick, who's really the father of tomato genetics. And here's a nicer picture of him. We owe this man a great deal of credit for developing tomato genetics, and he personally made most of the collections that are at the Tomato Genetics Resource Center in Davis. So just an incredible person. So why should we, let's go back. Why should we preserve the diversity of wild species? I hope to be convincing you of this. Well, okay, so we left this migration pattern here, and we've gotten a genetic bottleneck, right? Every time you take your seeds, you only take the very best seeds, and you transport them, and then you use those. So the genetic bottleneck is getting narrower and narrower and narrower. Okay. And now in the 20th century, wild germplasm traits are starting to be introduced back into the cultivated varieties. And it had a tremendous effect. Let me show you a graph here showing the increase in yield that occurred starting in about the 1940s, which was basically due to introduction of traits into cultivated tomato from the wild relatives. So it's come full circle now. We're introducing these traits back into cultivated tomatoes. And you can see that it's just had a huge effect. This slide you've already seen showing some of the disease-resistant traits that have been moved into cultivated tomato from wild relatives. But here's one that if you grow tomatoes, no, if you cultivate tomatoes, and I hope you all do, because as an old song says, the only 2 things that money can't buy is true love and a homegrown tomato. But all of your homegrown tomatoes will contain this trait from Solanum peruvianum, a wild species, and you would not be able to grow tomatoes in your garden in most places in the United States if it didn't have this trait associated with it. And so, let's see, so here's the nematodes are small worms that will cause this knotting and will be very bad for your plants. And whereas if they have the resistance trait, they'll be a nice root system. Okay. And, oh yes, just to remind me, this is important for other solanaceous crops as well. So things like peppers and eggplants also can use these traits from wild relatives. Here's another example of an important trait. This was introduced from one of the Galapagos wild species, and this trait is actually how the fruit is attached to the plant. Most tomatoes have this bend or a joint in here, and when you pull this off, you pluck this tomato off, it'll break right here and leave this hard part, and that's sort of a disaster when you're harvesting tomatoes. But if you breed in this trait from the Galapagos wild tomato, which is Cheesemanii, you get a jointless stem structure here, and the fruit will just pop off. Okay, we'll move right along. Here's an example of antioxidants are now considered to be very important, and here's another trait that's been passed in from wild tomatoes, high lycopene concentration. All right, I'll just put in a plug for the germplasm conservation. You're going to hear more about this from Chris here soon. But I want to leave with, again, another point that Dr. Benziger said, is that it's also really important to conserve wild species in situ. On this trip that we took to Peru, we found that where all the collections of Typhifolium had been made, they were gone. They were gone because of cultivation and we think climate change. So this species is being pushed up higher and higher into the mountains. And it's really very distressing, actually. And so I'm putting in a plug also for both kinds of conservation to be taking place with our wild relatives. So with that, I will end it, and we'll talk more about tomatoes later.
Yum! I don't know about you, but I'm getting hungry for some of that food. As I'm setting my timer here, a couple of things. 3, 7, 10. Now you should be writing those questions down because you're not going to get to eat any of that food back there if you don't have questions for the panel. And speaking of all this enthusiasm, yes, I'm getting thirsty. How about you? Yeah. Well, our next speaker, Stephen Menke from the Department of Horticulture and Landscape Architecture, trained at the University of Wyoming, is going to talk to us about the harvest of that favorite fruit, the grape. Stephen.
The history and genetics of grapes are a little bit divergent from some of the other things we talked about. As a woody perennial vine, they have some differences right away that you have to deal with, and they were widespread in their ancestral forms 500 million years ago. And yet, there's been some interesting challenges in terms of domestication and some lacks of bottlenecks and bottlenecks both, and we'll talk a little bit about that. So you cannot separate grapes and their domestication from fermentation. That just does not happen. It's not something you go out in the woods and say, oh, yummy. The wild grapes tend to be rather unpalatable, very high in anthocyanins and lots of bitter flavonoids. So they tend to be evolved on a domestic basis with the act of fermentation, which makes them a little unique. So what we have today are the uveitis, what they call true grapes, and their origin in Central Asia, as we talked about, but they also have origins in North America and in China as well. So it's a little bit strange that we have only to thank the true grape, or the vinifera, for most of our current industry in terms of wine, and yet there are a lot of other grapes in the world that evolved very nicely on their own. The main difference you'll notice in gross phenology is that the wild grape has a short and broad seed, whereas the cultivated vinifera grapes tend to have a pointed pip. Because of the particular patterns of domestication, of all done within one species in Europe and Central Asia, there are lots of cultivars that are all interfertile, which makes it a little bit of a different crop to deal with too. We do have a muscadine species in North America that does have a palatable fruit, although that depends on who you talk to in the wine world. There's documented evidence, Patrick McGovern at the University of Pennsylvania has done a lot of this work, that in the Kurish regions, in Georgia, in that area, 7,000 years ago, there were cultures that were already using wine as a part of their everyday culture. He's traced chemicals put together, such as pine pitch and the grape chemicals themselves, and he has